Hello, this is Dr. Goling again, and we're going to talk today about what's going on in section 7.5 and 7.6. In these sections, we learn two new rules, which are very powerful rules that allow us to make progress doing arguments, constructing arguments, in a way that, as I've said before, makes some of the rules that we've been using so far obsolete, not necessary. One of the things about conditional proof and indirect proof is that the name indirect proof and conditional proof, these names are somewhat misleading. And that's because conditional proof is really a rule. It should have been called something like conditional rule, or the rule of using a conditional argument, as we'll see. The same thing with indirect proof. The term indirect proof gives the misleading connotation that somehow the proof itself is an indirect proof. Now, really, as we're going to see, you can use conditional proof inside an argument and then continue with other steps that get you to your conclusion. And the same thing is going to be true with indirect proof. Anyway, let's talk about 7.5 first. We're going to show you how conditional proof works. Essentially, if we were to represent conditional proof using our symbols, we would say something like this. Conditional proof allows you to make an assumption, okay? If I assume that P is true, and I can show that Q follows from P, then I will be able to infer that P horseshoe Q. Basically what this is saying is, at any time I'm in the middle of an argument, if I make an assumption, so this is going to be called an assumption for CP, okay? An assumption for conditional proof. If I assume P, and P can be anything I want, if I assume P and I'm able to show that P somehow leads to Q, then what I can do is cut off this assumption. That's what this line represents. What this line represents is that I'm assuming something, and then I'm showing that if that thing is true, it follows that Q is true. I then cut off what's called the scope marker. This thing here is called the scope marker. And the reason it's called a scope marker is because it shows the scope or the range of the assumption that we started with. And this line over here represents the end point of that assumption. And what I'm saying is, given that I've been able to show that P somehow leads to Q, I'm going to be able to infer that if P, then Q, based on the steps that are in here and based on any previous steps that were in my proof. This is probably a little bit hard to follow without a specific example. Also, the book does things a little bit differently from the way I would do. What the book does, it simply has one line like this, indicating the scope of the assumption. Okay? My scope marker that I'm using here today is a little bit more pronounced. I have the arrow pointing to the assumption, and I also have something that cuts off the assumption, because P horseshoe Q does not require that P be true, okay? That's the idea of cutting off the scope marker here, that I'm showing that if P is true, Q follows. So when I infer that if P then Q, this no longer depends on P being true. Okay, this may be a little bit abstract to follow, so the best thing to do is to do some examples. And I'm going to use a couple of the examples that are actually inside the book. Again, we're in section 7.5. So let's suppose I'm given the following premises. I'm just going to make a little more room here. Okay, suppose I'm given the following premises. I have A horseshoe B dot C. That's a premise. I have B wedge D horseshoe E. That's also a premise. And I am trying to prove A horseshoe E. This is the first example that's given in the book in section 7.5. What I'm trying to prove is A horseshoe E. Okay. Now, if I were to try to do this using the rules that we've learned so far from 7.2, 3, 7.4, this might not be so easy to do. I mean, maybe it would be easy, but let's just try doing this proof using our new rule called conditional proof, or CP, okay? So the way CP works is, one way of doing it is, I could do something with this, like maybe I could do something like, I could do D wedge B, horseshoe E. This would be commutation on 2. I could do some other steps, and then I could say to myself, you know what, I'm going to do a conditional proof. I'm going to use the rule of conditional proof. Actually, let's just erase this. This was really not necessary. So the way you would do a conditional proof is, if you're looking at the conclusion, this is a conditional statement. So one way of proving a conditional statement is to use conditional proof. The result of a conditional proof always has to be a conditional statement, even though the argument can continue further on, as we'll see later. But right now, let's see, okay, if I assume A, I'm going to assume A, and I'm going to try to derive E, and then, let's make this E better, okay? If I assume A, and now I can show somehow that that leads to E using these premises, all right? Then I can cut off the scope marker and say, I got to A horseshoe E. I've shown that if A is true, then E is true. So can I do that? So the nice thing about conditional proof is it gives you an extra step to work with. That's one nice thing about it. Now I should put down the justification over here. The justification is assumption. I'm going to abbreviate that as ASS dot CP. Or you could just be a little bit more plain and just say ACP. Okay, basically what ACP means is assumption for conditional proof. I'm letting myself assume something only temporarily. You know, you can't just add premises to your argument that weren't given to you, but you are allowed to assume something temporarily. If you can show, assuming A is true, I can get to E, then I know I can infer that A horseshoe E. So now I have an extra premise, and now this is going to make this argument flow a little bit more easily, because since I have A, and over here I have A horseshoe something, so now I use modus ponens. So generally speaking, inside the scope marker, you would be using the old rules, the rules that we've learned already. So this would be a modus ponens on 1 and 3. I would get B dot C. Okay, I could now simplify this conjunction to get B. I can now, I see I'm getting closer to E. I need to just use addition, B wedge D. And now I can get E by modus ponens on 2 and 6. Okay, and now I just fill in my numbers. This is step 8. And now I'm going to say, as my very last step, conditional proof. Now here, notice I'm not saying ACP. ACP is for the assumption, right? When I assumed A, my justification was that I am assuming something for conditional proof. Now I say CP, which stands for conditional proof, 3 through 7. Okay, and that's how I might get to A horseshoe E using the rule of conditional proof. So, if you have questions about this, I hope you'll ask. I think the best thing for me to do is just keep doing some more examples. We're going to see now, again, I just want to remind you that the conditional proof does not necessarily have to be the last step in a proof. It could continue. Like I could go on and say, okay, not E horseshoe, not A by transposition on 8. Okay, maybe if this was my desired conclusion, I would just go on further. So conditional proof is not necessarily the last step in a proof. It can be used at any time in the middle of a proof, and in fact, we're going to see some examples of where you can actually do a conditional proof inside another conditional proof. But before we get to that example, let me show you a different example where we're going to see that you can use conditional proof twice at separate occasions in one argument. That's the next example in the book. Let's see here. We've got G horseshoe H dot I. This is the premise. We have J horseshoe K dot L. That's the premise. And we have, let me just check this out here. We have H wedge K. Okay, just want to check this out. Excuse me. Okay, so now this is not a conditional, right? This is a wedge, but I'm still allowed to use conditional proof in the middle of my proof if I find it helpful. So I'm going to be optimistic. I'm going to put H, I don't know how many steps this is going to take, so let me erase these numbers, but hopefully I'm going to get H wedge K somewhere at the end of this proof. Now, what can I do with with these premises? Okay, well, what I'm going to do is I'm going to try to do two different conditional proofs here. I'm going to say, you know what, I'm going to be able to prove that if G is true, I'm going to be able to prove H, and I'm also going to do something like this. I'm going to say, if J is true, I'm going to be able to prove K. That's going to be pretty easy because if G is true, H dot I is going to be true, and then I would just simplify to get H. So once I have G and J over here, I'm now going to be able to, once I have G horseshoe H and J horseshoe K, excuse me, this one goes inside here, J horseshoe K. Okay, I see what happened. I'm missing a premise. I'm sorry. This was number 3 was G wedge J. Okay, now this is making more sense to me. I'm sorry. I neglected to write the third premise, which is really dumb. But if you don't have all your premises, you're probably not going to be successful in getting to the proof. So, okay, you have G wedge J over here. So now, if you can prove G horseshoe H and J horseshoe K separately, this is going to be an assumption for conditional proof. And how do I get H? Pretty easily, because I have modus ponens on 1 and 4. And now I simplify to get H. And this is going to be a CP on 4 through 6. This is going to be step 8, another assumption for conditional proof. I'm assuming J here. I can get K dot L by a modus ponens. Modus ponens on 8 and 2. K here is number 10. This is a simplification on 9. Now I have J horseshoe K. This is step 11. This is a CP on 8 through 10. And now I have G wedge J, J horseshoe, G horseshoe H, and J horseshoe K. So technically what I should do is put those two conditionals on the same line. I have G horseshoe H and J horseshoe K. This is conjunction of 11 and 7. And now I can get what I was looking for, which is H wedge K, and that is a constructive dilemma on 12 and 3. Okay, so the strategy here was I'm trying to prove a disjunction. One of the ways of getting to a disjunction is by using constructive dilemma. In order to have constructive dilemma going, I already have G wedge J, and I needed to get G horseshoe H and J horseshoe K separately, put them on the same line, and then do a constructive dilemma to get the desired conclusion. So that's another illustration of conditional proof, and here we did two separate conditional proofs. Now here's a very important rule about how conditional proof works. Once this scope marker is closed off, you're not allowed to go back in there and use premises from the middle of that scope marker, because the idea is that everything that's inside the scope marker is based on an assumption that G is true. Now G was not a premise, it was only an assumption. So therefore, once I come to the conclusion, not the final conclusion, but once I've made this inference that G horseshoe H is true, I've closed off my scope marker. I'm not allowed to go inside the scope marker and use any of these steps once the scope marker is closed off, otherwise you would be able to prove ridiculous things. Okay, the book has some illustrations of that. Let's see another example of conditional proof. And this example that I'm going to do on the board is the next one in the book. Try to write all the premises down this time. I'll do the numbers. Okay, the next one in the book is L horseshoe. We have two premises here. L horseshoe, here's the premise number 1. L horseshoe M horseshoe N wedge O. That's one premise. Then we have M horseshoe not N. That's another premise. And we're trying to prove L horseshoe not M or O. All right. L horseshoe not M or O. That is what we are trying to prove. So, I look at the conclusion here. I say to myself, this is a conditional. Why don't I try conditional proof? Anytime you're trying to prove a conditional statement, anytime your conclusion is a conditional, it always makes sense to try conditional proof and see if you can do it, because that gives you an extra step. It gives you an extra formula to make use of. So you would always assume the antecedent and try to derive the consequent. So I would go step 3, assumption for conditional proof. I'm going to make my scope marker indicating that I'm going to assume L, cut off the scope marker, and put the consequent on the top of the scope marker, or in this area right here, not M. Well, this doesn't need a parenthesis now, right? We have not M wedge O. That is what we are shooting for. And then the very last step is going to be L horseshoe, not M wedge O. This would be a CP on steps 3 through whatever this numbered step is. Okay? So, now that I have L, see, I can do a modus ponens on 1 and 3. Again, inside here, very often it's going to be the same rules. I think in this example, one way of doing it is going to be having another conditional proof in here, because working backwards, remember that not M wedge O is the same thing as M horseshoe O by implication. So if I can get to M horseshoe O, I can then get to not M wedge O by implication on whatever this step is. Don't know yet what that number is, but now I look at M horseshoe O. This is a conditional. So I can use conditional proof to try to get M horseshoe O. How would that work? I'm going to assume M. See, now I'm going to use a scope marker inside another scope marker. This is assuming that L is true, and now I'm also assuming that M is true. So this would be step 4, another ACP. And now I would try to get O. And I'd be able to use anything that's above the scope marker, as long as it's not inside another scope marker. These premises are things that I can use. So I can use L, I can use M. So over here, I could say, well, I have a modus ponens. I have not N, modus ponens on 2 and 4. And now I can also get by a modus ponens that thing, M horseshoe and wedge O. So I might need a little more room here. But step 6, I do a modus ponens on 3 and 1. I get M horseshoe and wedge O. This is modus ponens on 1 and 3. Now I have another modus ponens 4 and 6. That's N wedge O by modus ponens on 4 and 6. And now I have a disjunctive syllogism on 5 and 7. And that gets me O. Disjunctive syllogism on 5 and 7 gets me O. And now I'm just going to fill in the numbers. This would be number 9 is CP on 4 through 8. And this is an implication on 9. And this is 11, CP on 3 through 10. Okay, so this example has a conditional proof inside another conditional proof. I assumed that L is true, then I made another assumption that M is true. I showed that if I assume M, I can get to O, so that means I can infer M horseshoe O. And then I continued with my rule of implication, and that shows that if L is true, then M wedge O is true. And then I concluded the proof by saying, if L, then not M wedge O. So that's conditional proof on 3 through 10. Okay, so let's see some of the exercises. Basically, the exercises look to me like they're all pretty much doing proofs. I'm talking about Roman numeral 1 here in exercise 7.5. So what I would suggest is that you pause the video and try doing some of the exercises from 7.5 Roman numeral 1. See if you can do any of those proofs. Okay, now I'm going to show you some of the proofs from 7.5 Roman numeral 1 on the board. I'm not going to do all of them, so you'll have some to do on your own, but let's try a few of them. Okay, we'll try an easy one, a relatively easy one first. That would be number 1. What do we have here? N horseshoe O, N horseshoe P. N horseshoe O, N horseshoe P. Those are horseshoes. And then we have N horseshoe O dot P. This is the premise. This is the premise. N horseshoe O dot P. Okay, well, I'm thinking to myself, how am I going to get N horseshoe O dot P? Now, if you didn't have the rule of conditional proof, how would you do this? What would you do? You'd have to conjoin the two statements, and then you'd have to do some kind of implication, and then maybe rearrange the parentheses using association. This would not be easy to do using the rules from 7.4. Okay, but with conditional proof, this is a relatively easy proof. I look at my conclusion, I see that it's a horseshoe. Right away, I think conditional proof. To use conditional proof, assume the antecedent, try to derive the consequent. What's the antecedent? It's N. So that would be a good first step. I'm going to assume N. Again, the way I write my scope markers are like this, a little different from the book. You can use either way you want to. I just find this more helpful because it's more clear as to what's going on. But if I assume N, I'm going to try to derive the consequent, which is O dot P. And then the last step in the proof is going to be if N, then O dot P. And that would be a conditional proof on 3 through whatever this numbered step is. Now this is very easy because we're seeing modus ponens here. You're going to see a lot of modus ponenses in these arguments. What you have is you're trying to get to O and P. All you need is 2 modus ponenses in conjunction. N horseshoe O and N by modus ponens on 1 and 3, we get O. All right, and by a modus ponens on 2 and 3, we get P. Right, you see that? I hope so. So now 6 is just conjunction. Conjoin 4 and 5, you get O dot P, and now 7 is the final step, conditional proof on 3 through 6. So that's how you do number 1. Let's try a few more examples. Okay, I'm going to skip down a little bit, maybe try one that's a little harder maybe. How about we try, I don't know, I feel like trying number 5. It just has one premise, A horseshoe, not A wedge E. A horseshoe, not A wedge E. It just has one premise. And we're trying to prove A horseshoe F. Well, that looks interesting. That's a very interesting argument because F does not even occur in the premises. So you might think something, maybe this is a mistake. Is there a typo here? Well, maybe. I don't think so. When I look at A horseshoe, not A or E, my goodness, that might be a typo. I wonder about this. How am I going to be able to prove A horseshoe F? I have a feeling this might be a typo, because if I assume A, this is a conditional, I'm going to assume this for ACP, try to show that F is true. I could do a modus ponens, I would get not A wedge E, modus ponens, and then I could do a double negation on number 2. The reason I'm doing that is because I see, first of all, this is NP on 1 and 2. The double negation on 2 would give me not A, so now I can use a disjunctive syllogism to get E. Disjunctive syllogism on 4 and 3. So how in the world am I going to get F? I'm going crazy here, thinking that perhaps this is actually, I don't see how we're going to get F out of A. So I think the thing to do would be to do a truth table method for this to test whether this is really a valid argument. I think it's an invalid argument because, yeah, I think there's a mistake here in the book. I apologize on behalf of the book. I think this was supposed to be an E, okay? And that way, what it is we're just going to do this, okay? I think there's a typo in the book on number 5, and this is supposed to be A horseshoe E by a CP on 2 and 5. Okay, because if A is true, if A is false, and if this were F over here, I'm just thinking that that does not look like a valid argument to me. If A is false, if A is true, and F is false, this would be false. Now let's see if we can come up with assignments that would make that, that's false. And so if we say this is true, as long as E is true, this would be false, this would be true, and this would be false. So there is really a counterexample. So the argument in the book where you have A horseshoe F is just a mistake. It should have said A horseshoe E. And this is the way it's supposed to be done. Let's try a different example, hopefully one that the book didn't make a mistake about. And maybe in your book this was corrected. I'm curious as to whether that's true. Perhaps you could email me if in your book the conclusion of number 5 is supposed to be A horseshoe E, not A horseshoe F. Okay, let's just try a different example. How about we try number, let's try number 11. Okay, I'm going to try number 11 in the book. This is M horseshoe K horseshoe L. And we have L wedge N horseshoe J. And we're trying to prove M horseshoe K horseshoe J. All right, M horseshoe K horseshoe J. Okay, so how do we do this? I look at the conclusion. Now remember, this, the other strategy we have is not just to look at the conclusion, but to milk the premises for all they're worth. But with these premises, there's nothing really obvious to do that's going to lead to this. Maybe you could do some kind of exploitation. I don't know. Again, once you have conditional proof, you should use it whenever you can. I'm going to assume M. I'm going to try to derive K horseshoe J. And then my last step will be if M, then K horseshoe J. This will be a CP of 3 through whatever this is. Now, this is going to be assumption for conditional proof, ACP. Now, I look at this, I see, hey, look, this is a conditional also, K horseshoe J. So I could do another conditional proof inside here. I'm going to assume K and try to get to J. Okay, so this would be another assumption for conditional proof. This would be step 4. Now, I have a modus ponens here, 1 and 3. All right, I'm supposed to be able to notice the modus ponens very readily. Modus ponens on 1 and 3. That would give me K horseshoe L, right? That's the consequent over here. And now I have another modus ponens on 4 and 5, this time to get L. Modus ponens on 4 and 5. And now, can I get J out of L? I didn't use 2 yet. Is there some way I can use 2? I have L. Can I get that antecedent? Yes, I can by using the rule of addition. So let's just go L wedge N. You're allowed to wedge on or add addition. Addition on 6 gives me L wedge N. Now I can get to J by modus ponens on 2 and 7. So I now have J, and now the rest of it is just filling in the numbers. I showed that if K is true, I can get to J. Here's step 9. This is the CP on 4 through 8. And this is going to be the last step, CP on 3 all the way through 9. Okay, and that is number 11. Okay, now I'm going to ask you to do proofs from 7.5 and see how well you do. And if you have any questions or problems, email and or call me. I'm going to go on now to 7.6, okay? In 7.6, you learn another very powerful proof or rule. It's really a rule, which is called indirect proof. So we're going on now to 7.6. What is indirect proof? Okay, so we're in 7.6. We're talking about indirect proof. And this has another name. It's sometimes called reduction to absurdity, or in Latin, reductio ad absurdum. In some logical systems, you would find that this is called reduction to absurdity. In this system, it's called IP. Indirect proof, reduction to absurdity could be RA, or sometimes it's called RAA, reductio ad absurdum. But anyway, let's stick with the name indirect proof. Now, I don't think it's the best name. I think reduction to absurdity would be a better name, but the strategy of the proof, or actually, again, it's really a rule, not necessarily a proof, because a proof is an entire argument, right? A rule is something you can use in the middle of an argument to make progress. But the way the rule is represented is as follows. Let's suppose that if I assume P, I could somehow show that it leads to a contradiction. Somehow P leads to Q and not Q. Okay, Q and not Q is a contradiction. We know that Q and not Q is something that cannot be true. It's a logical contradiction. using the definition of the truth table method that a contradiction is a formula which will always come out false under the major operator. If you do a truth table for Q and not Q, it's always going to be false, right? So Q dot not Q is, you might say, it's the prime case of a contradiction. I'm saying Q and not Q at the same time. That cannot possibly be. That's an absurdity. But if P leads to an absurdity, that means that I know that not P has got to be the case. Okay, so this is going to be the structure of an indirect proof. This is going to be an assumption for indirect proof. So we say AIP. However, I get to Q not Q is going to involve some other steps. And then I'm going to say indirect proof on whatever step P is, all the way down to getting to Q and not Q. So one of the things about indirect proof is it always allows you to tack on a tilde to the thing that you assume. Now the thing that you assumed, again, P could be a very long formula. It could be not A, wedge B, biconditional C, horseshoe Q, whatever, something very, very long. But whatever P is, the conclusion of an indirect proof is going to be, it's not the case that whatever P was. Now, that's why it's called indirect proof. It's called indirect proof because you're proving that something is not the case. You're taking something and showing that it leads to a contradiction, so therefore the opposite of it is true. And that's why it's called indirect proof. However, it's really not so important to remember that. You just need to know it's called IP, and the structure is, if I can show that a certain formula leads to a contradiction, then I know that I can tack on a tilde, close off the scope marker, because again, the conclusion doesn't depend on P's being true. I'm not saying that if P is true, then I know that not P is true. I'm saying if P is true, it leads to a contradiction. Therefore, I know without any assumptions that not P is the case. Okay, let's see how this works in practice. Again, some of this is a little hard to follow without seeing a specific example. So again, I'm going to do some examples on the board, and then you're going to have to try to do some of the proofs on your own from the end of 7.6. Again, it's going to be Roman numeral 1. Okay, so the homework is to try to do 7.5 Roman numeral 1, as many as you can do, and 7.6 Roman numeral 1, as many as you can do. Okay, so let's just try some of the examples that are in the book. I'll just illustrate how these work. Let's do the one that's in the book. On the board, we have, here, suppose you have the following steps: A wedge B horseshoe C dot D. This is premise number 1. Again, I always write premise, and then premise number 2 is C horseshoe not D. And I'm being asked to prove not A. All right? This is a premise. I'm being asked to prove not A. Okay, so what can I do here? Well, in this case, I'm being asked to prove not A. So right away, I think of indirect proof. I say to myself, you're asking me to prove not A, you know what I'm going to do? I'm going to prove it indirectly. I'm going to do this. I'm going to assume A. I'm allowed to do that. Assumption for indirect proof. I'm going to show that somehow this leads to a contradiction. Some formula that's going to look like this. Blank and not blank. I don't know yet what the blank is going to be, but I have set up here the framework of a contradiction. Something, and it's not the case that whatever that something is. The exact same thing here is going to be over here. And then I'm going to say not A. That's going to be the final step in the proof. If I can show that A leads to a contradiction, I'm going to say, well, by indirect proof, I've shown that not A has got to be the case. So here's step 3. Now what I need to do is try to get to a contradiction. Okay? Well, how do I get to a contradiction? First of all, use the strategy of milk the premises for all they're worth. Is there some way I can get something out of, I have A, I see that A is sitting in here, it's wedged onto a B, so to get the antecedent of number 1, I just need to use addition. A wedge B, addition on 3, and now I can do modus ponens, C dot D, modus ponens on 1 and 4. And I can simplify C dot D to get C, and I can simplify it to get D. This is simplification. Simp on 5, simp on 5. Okay, I have C, I have D. Now, I use number 1, but I haven't made use of number 2 yet. And I have C over here, so I can do a modus ponens to get not D. I see a contradiction coming here. I have not D by a modus ponens on 6 and 2. And now I can conjoin D and not D. I'm conjoining 7 and 8. That was the contradiction that I ended up finding. Conjunction on 7 and 8. And now I simply fill in the numbers. This is step 10, IP on 3 through 9. Okay, so again, the strategy is when using indirect proof, you can assume something, you can assume anything you want. In this case, what was convenient to assume was, hey, I'm going to assume A and show that it leads to a contradiction. That way I get not A. How did the contradiction come about? Simply by using the old rules, I found D and not D. That was my contradiction. Close up the scope marker and finish the proof with the conclusion not A. Indirect proof based on steps 3 through 9. Okay, now like we saw with conditional proof, you can have a conditional proof inside a conditional proof. You can have an indirect proof inside a conditional proof. Okay, you can have a conditional proof inside an indirect proof. You can have multiple, sometimes they're called nested examples or nested conditional proofs where you have one proof inside another proof inside another proof. And again, I keep harping on this. The word proof is a little misleading. It's really a rule that you're using at any time in the middle of a proof. I would prefer to get a different name, maybe reduction to absurdity as a rule. But anyway, it really doesn't matter what the name is as long as you keep it straight. Let's do another example, or actually what I was thinking was that you can pause the video and try one of the examples from the exercises in the homework. Okay, so let's look at the homework together from 7.6. Again, you should read the chapter. There's a lot of illustrations in the chapter. I will simply ask you to pause the video, do some of the reading if you can, and try to do some of the exercises from Roman numeral 1, 7.6. Okay, so now I'm going to continue doing indirect proof. Now let's try number 2. That might look a little bit bizarre. There's no tilde in the conclusion, so how am I going to use indirect proof? Well, I'll show you a little trick here in a minute. Let's get number 2 up on the board. Okay, we have K horseshoe, R. Where we have this. K horseshoe R is a premise. And we have R wedge M horseshoe N. R wedge M horseshoe N. Okay, I'm doing number 2 from Roman numeral 1. This is a premise, and we're trying to prove N. Okay, now, you might say, well, how am I going to use indirect proof? I'm not being asked to prove something that has a tilde hanging out in front of it. So how can I use indirect proof for that? So the answer is that you're going to use indirect proof here, what you would do is, I'll tell you what, I'm going to assume not N. Okay, I'm going to assume the negation of what I'm trying to prove, show that that leads to a contradiction. Hopefully it will. It should if the proof is correct and there's no typos. Okay, so I'm going to assume not N. Show that that leads to a contradiction. And then I'm going to conclude, well, if this leads to a contradiction, that means not N, right? So I am tacking on a tilde to what this formula is. And then the very last step will be take off the tildes by double negation. Okay, remember double negation, that's dn over there, allows you to take off 2 tildes from any formula. So this is going to be IP, hopefully, on 3 through whatever this step is. Now I have another formula, I have not N, and look at this. I can see right away I have a nice modus tollens to do. Remember, modus tollens is the rule that says if you have a conditional and the negation of the consequent, you can get to the negation of the antecedent. So that's going to be not R wedge M. Modus tollens on 2 and 3. And now with not R wedge M, this is a very powerful statement because I can break this down using the rule of De Morgan. Remember, the rule of De Morgan says that not R wedge M is going to be equivalent to not R and not M. That's De Morgan on 4. And now I can break this down. I have not R. That would be a simplification on 5. And now I can do a modus tollens on 1 and 6 to get not K horseshoe K. And here's something that, as you do more of these, you sort of get the hang of it. This statement right here is a contradiction in and of itself, because this is saying it's not the case that if K, then K. That doesn't make any sense, because K horseshoe K is actually a tautology. Okay, a tautology is a statement that has to be true. So how I'm going to show that that's a contradiction by doing the following. We have a implication. Remember, this is a horseshoe. I can go not K, wedge K. I'm changing the horseshoe to a wedge and tacking on a tilde to the antecedent. This is implication. And now I have another case of De Morgan. This is not a wedge, so I can do not K and K, not K. Not K and not K. That is De Morgan. And we could consider that a contradiction because it says it's not the case that not K and not K. If we want to flip it around and do double negation, we could do that. I'm running out of room here, so perhaps we could do, just to make it clear, we could say, well, we have K and not K by double negation on 9, and there's your contradiction. So there actually is a little room for that. Let's do that. We'll put it in right here. Taking off the 2 tildes, I have K and not K. That is a double negation on 9. And now I have my contradiction, which means that not n can be negated. This would be 11, this would be 12, and filling in the numbers, that would be 3 through 10, and this would be double negation on 11. I think I've got my numbers right, even though, sorry, it's a little bit small in there. Okay, so again, the strategy was, I'm not going to be able to use, how am I going to be able to use indirect proof? I'm going to assume the opposite of what I'm trying to prove, show that that leads to a contradiction, tack on a tilde to the assumption, and then go to n by a double negation on step number 11, taking off the two tildes. Okay, so that's exercise that was number 2. All right, let's see, let's show you something a little different maybe. Let's try number 6. Try it on your own. Try to do number 6. And then either when you get stuck and can't proceed, or if you finish it, turn the video back on. I'm going to do number 6 on the board right now. Number 6. Okay. We have not A, horseshoe B, and C. A. We have D, horseshoe, not C. And we're trying to prove D, horseshoe, A. Okay, so, excuse me a moment. All right, not A, horseshoe, B, and C, D, horseshoe, not C, and then D, horseshoe, A. Okay, so the natural thing to do here is, I'm looking at the conclusion, I see that this is a horseshoe, I'm going to assume D, and I'm going to try to derive A. Assume D, try to derive A, and then I would get D horseshoe A by CP. So now you're being asked to use both conditional proof and indirect proof, possibly in this one. Okay, so here is step 3. This is an assumption for conditional proof. I'm going to try to get to A, and then I'll go to D horseshoe A. Well, right away I see a modus ponens. If you see modus ponens, you should definitely do them. Modus ponens on 2 and 3. That's a 2. Okay, I'm getting not C. Okay. What should I do now? Okay, whoops. Anyway, just had a window blow open here. What should I do now to get A? So here's something that I could do. What I could do is, in order to get A, I'm going to do my little trick, which is I'm going to assume not A for indirect proof. I'm going to show that that leads to a contradiction, hopefully. And then I'm going to go not A, adding a tilde to the assumption, and then by double negation, I'm going to get back to A. So I hope you can see this. This is assuming not A for an indirect proof. Get to some kind of contradiction, blank and not blank. That's going to be a contradiction that allows me to tack on a tilde to the not A, and then I'll do double negation to remove the two tildes, and then I'll have A, then I'll go D horseshoe A by conditional proof on whatever step 3 through whatever step is A. Okay, see, now I have a not A to work with. So I have a modus ponens. I can get B dot C by a modus ponens on 1 and 5. And now I can get C by simplifying. Simplification on 6. And now I can conjoin 4 and 7. C and not C. Conjunction. See, I am allowed to use C because C is inside, it's inside a scope marker, but I'm still inside that scope marker. Once the scope marker for C not C got cut off, I wouldn't be able to use it. But even though I'm in this scope marker, this whole thing is inside this scope marker, and not C is included in there. So I'm allowed to use step 4, conjoin it with step 7. I have a contradiction. Now the rest is filling in the numbers. This is IP on 5 through 8. And then this is double negation on 9. And then this is step 11, where you get CP is 3 through 10. Okay, so that is example number, what was that one? That was example number 6. All right. Okay, so we've been going on for about an hour now, so I'm going to stop. We've talked about 7.5, 7.6. The homework is to do exercises from Roman numeral 1 in 7.6 and Roman numeral 1 in 7.5. Technically speaking, this is our last lecture class. However, I'm willing to do some kind of lecture that involves reviewing all of the material for the final. Now, I did send you a little email describing the breakdown of points on the final. There's truth tables, there's translations of sentences, and then there's proofs. So if you have material that you want to go over, if you have questions, now is the time to, I don't mean right this second, but email me, call me, so that I can help you by going over either in the lecture form or one-on-one any of the material that you feel weak on. So I'm hoping to hear from you so I can get some clue as to what would be beneficial for you in terms of my going over material. I could spend time doing more proofs. Probably that would be helpful. I could spend some time going over the truth tables, translations. Your questions would be very helpful for me to decide how best to have a review before we actually get to the final exam, which is next Thursday, okay? So I'm going to call it quits here, but again, be in touch with me about what you'd like to go over. And if you have any questions on anything I've talked about today, please indeed let me know. I hope you're well, and I hope to hear from you real soon. Bye now.